Close your eyes for a moment. Take a deep, slow breath. Imagine floating above our beautiful, noisy world. You are drifting higher and higher, leaving the chaotic sounds of the city far behind. We are entering a realm of perfect peace. But here is a fascinating paradox to consider. We often imagine the universe as a loud, dramatic battlefield of exploding stars and roaring rockets. Hollywood has taught us to expect deafening blasts. Yet the reality is far more soothing. In the vast expanse of the cosmos, the most violent events are enveloped in a perfect, eternal hush. Tonight, we will uncover why space refuses to carry the sound of an explosion. We will replace the loud myths with the calming truth of physics. So, settle in, relax, and let the silence of the stars wash over you. To truly appreciate the majestic silence of the cosmos, we must first look at the noisy world we call home. Here on Earth, sound is a constant companion. It is the wind rustling through the trees. It is the gentle patter of rain against your window. Ancient philosophers like Aristotle believed that sound required a medium to travel, and they were absolutely right. Sound is simply a mechanical wave. It is a vibration. When an object moves or explodes, it pushes against the air molecules around it. These molecules bump into their neighbors, creating a rippling chain reaction. This invisible wave travels through the thick, comfortable blanket of our atmosphere until it gently taps against your eardrum. Your brain translates this delicate physical touch into what you hear. Sound needs a bridge to cross from the source to you. It needs air, water, or solid ground. Without this bridge, sound is trapped. It is born, but it has nowhere to go. And that brings us to the edge of our atmosphere, where the air simply runs out. The grand illusion of cinema. Let us begin by breaking a famous myth. We often believe that a spaceship exploding in the dark void produces a terrifying boom. Imagine a bright, vivid illustration on screen, a massive spacecraft bursting into a sphere of orange fire, while on one side we show a roaring cinematic explosion, and on the other, a completely muted, perfectly silent expansion of debris. In movies, sound designers add heavy bass and sharp cracks to make us feel the impact. But if you were floating just a few miles away in a spacesuit, you would witness a spectacular light show in total silence. The energy is there, the destruction is real, but the bridge of sound is missing. The movie magic tricks our senses, but reality offers a much deeper, more peaceful experience. The anatomy of a silent wave. What exactly is a sound wave? To understand this, picture a calm pond. If you drop a stone into the water, you see ripples expanding outward in perfect rhythmic circles. Sound works the exact same way, but in 3 dimensions. Imagine an on-screen graphic showing glowing particles bumping into one another in slow motion. This is called compression and rarefaction. An explosion pushes particles tightly together, and then they pull apart. But in the deep cosmos, there is no pond. There is no water. There are no particles to compress. When a star explodes, it releases an unimaginable amount of energy. It throws out light, heat, and radiation. But without a physical medium to carry the physical push, the acoustic wave simply cannot form. It is a dance with no dancers. The comforting blanket of Earth. Why is our world so loud? Let us appreciate the unique acoustics of our home planet. Earth is wrapped in a dense, heavy layer of nitrogen and oxygen. Imagine a beautiful animation of our blue planet, glowing with a soft, protective atmospheric halo. Down here at sea level, there are billions of trillions of gas molecules in every single cubic inch of air. They are packed together like passengers on a crowded train. When a volcano erupts or a bomb detonates on Earth, it forcefully shoves these densely packed molecules. Because they are so close, the energy transfers instantly. Sound travels at about 760 miles per hour through this thick soup. This dense blanket is what allows us to hear the symphony of life. It is a rare privilege in a quiet universe. Crossing the silent threshold. What happens when we leave this dense blanket behind? Let us take a journey upward. Imagine an illustration of a rocket slowly ascending through the clouds, the sky turning from bright blue to dark indigo, and finally to deep black. As we rise higher, the air begins to thin. The molecules drift further and further apart. By the time we reach the Kármán line, about 62 miles above the Earth, the atmosphere is incredibly fragile. Sound waves struggle to survive here. If an explosion were to happen at this altitude, it would sound like a faint, muffled whisper. The molecules are too far apart to effectively pass the message along. The chain reaction breaks down. We are entering the realm of the vacuum, where silence claims its territory. The true nature of the vacuum. We often mistake the vacuum of space for an empty, boring void. This is a common myth. Many think space is completely devoid of anything, but let us clear that up. Imagine a beautiful, deep-field image of space, sprinkled with distant galaxies, with a counter showing the sparse atoms drifting between them. A vacuum simply means an area with very low pressure and very few particles. It is not perfectly empty. There is interstellar dust, wandering hydrogen atoms and cosmic rays. However, these particles are scattered so incredibly far apart that they barely ever interact. If one atom gets pushed by an explosion, it might travel for miles before it ever hits another atom. This extreme isolation is why sound cannot propagate. The chain of communication is permanently broken. A star's silent death, the supernova. Now, let us witness the most powerful explosion imaginable. Imagine a massive star, hundreds of times larger than our Sun, reaching the end of its life. Picture an incredibly detailed simulation of a star collapsing inward, then rebounding in a flash of blinding, kaleidoscopic light. A supernova releases more energy in a few seconds than our Sun will in its entire lifetime. It blasts heavy elements out into the cosmos at a fraction of the speed of light. Yet, this apocalyptic event is utterly silent to a distant observer. The shockwave of plasma and radiation expands violently, but it does not carry an acoustic boom. You could watch the destruction of an entire solar system, and all you would hear is the rhythmic beating of your own heart. The secret acoustics of a spacesuit. But what does an astronaut actually hear? Let us address a fascinating nuance. If space is silent, is an astronaut completely deaf to the outside world? Imagine a close-up illustration of an astronaut floating outside the International Space Station, working with heavy metal tools. The astronaut is surrounded by a vacuum, but they are not in one. Inside the suit, there is air. When they strike a metal bolt with a wrench, they don't hear the sound traveling through space. Instead, the vibration travels through the metal of the wrench, into their bulky glove, up their arm, and into the air inside the helmet. This is called bone conduction and structural vibration. They hear a dull, heavy thud. They hear their own breath. They hear the hum of the suit's fans. They carry their own tiny, noisy world with them into the void. The myth of the roaring engine. Let us debunk another persistent cinematic myth, the roaring rocket engine. We have all seen movies where a spacecraft zooms past the camera with a deep, thunderous rumble. Picture an animation showing a sleek spaceship firing its thrusters in deep space. If you were floating in the vacuum, watching it pass, what would you hear? Absolutely nothing. The hot, expanding gases leaving the rocket nozzle are incredibly dense for a brief moment, but they instantly disperse into the limitless vacuum. The exhaust dissipates so rapidly that no sound wave can reach you. The pilot inside the ship feels the vibration through the metal hull, but to the outside observer, the ship moves like a silent ghost. It is a graceful, quiet ballet of orbital mechanics. The silent strike of a micrometeorite, the danger of silence. Because space is silent, it changes how we perceive danger. Imagine an illustration of a tiny, pebble-sized rock traveling at 20,000 miles per hour, striking the solar panel of a satellite. On Earth, a high-speed impact like this would produce a deafening explosive crack. In space, there is no acoustic warning. The panel shatters in total silence. The energy of the impact turns into heat and kinetic destruction, but no sound is radiated away. Astronauts must rely on visual cues and advanced sensors to know if their ship has been hit. The silence of space is deeply peaceful, but it also means the universe does not announce its hazards. You must remain watchful in the quiet. Electromagnetic waves versus mechanical waves. How do we communicate in the silence? If sound cannot travel, how do astronauts talk to Earth? We often confuse sound waves with radio waves. Let us separate them clearly. Imagine an animation showing slow, physical sound waves bouncing off a wall, contrasted with fast, glowing, squiggly lines of radio waves zipping through the stars at the speed of light. Radio waves do not need air. They are part of the electromagnetic spectrum, just like visible light. They are ripples in electric and magnetic fields, not physical pushes of matter. An astronaut speaks into a microphone, the helmet translates the physical sound into a silent radio wave and shoots it across the vacuum to Earth. Down here, speakers turn it back into a physical sound. We use light to send our voices across the silent dark. The art of sonification, hearing the invisible. You might have seen news articles claiming NASA recorded the sound of a black hole. How is this possible if space is silent? Let us uncover the magic of sonification. Imagine an illustration of a complex graph of light curves, slowly transforming into a musical staff with floating notes. Telescopes capture silent data, light, radiation, and magnetic fields. Scientists take this mathematical data and assign audible pitches to it. A bright flash of light might become a high-pitched ping. A slow magnetic pulse might become a deep, rumbling bass. This is called sonification. It is not actual sound captured from space. It is a translation. It is a way for our human ears to comprehend the complex, invisible data of the cosmos. It is the music of mathematics. The eerie chorus of Jupiter. Let us listen to a famous example of this translation. The Voyager spacecraft captured some of the most haunting audio ever released. Imagine a beautiful, swirling illustration of Jupiter's massive auroras, glowing in neon blues and purples. Jupiter has an immensely powerful magnetic field. As charged particles from the Sun slam into this field, they create intense radio emissions. They are silent in reality, but when NASA translated these radio waves into sound waves, it sounded like an eerie, sweeping, ambient choir. It sounds like the wind howling through a desolate, frozen canyon. These sonifications allow us to feel the power of Jupiter's magnetic storms. They give a voice to the silent giants of our solar system. The singing black hole of Perseus. But there is one remarkable exception in the universe, a place where actual mechanical sound waves do exist in space. Let us travel to the Perseus galaxy cluster. Imagine a colossal, glowing cloud of superheated gas, millions of light-years across, with a supermassive black hole at its center. This gas cloud is thick enough to act as a medium for sound. The black hole sends out immense jets of energy, pushing against this gas. It creates real pressure waves, real sound. Scientists have calculated the pitch of this cosmic hum. It is a B-flat. But it is a B-flat 57 octaves below middle C. It is a pitch so deeply low that the human ear could never, ever hear it. It is a silent song played on a galactic scale. The false density of beautiful nebulae. We often look at photos of nebulae and imagine them as thick, swirling clouds of colorful smoke. This is a beautiful visual myth. Imagine an illustration of the Orion Nebula, bright pink and blue, shimmering in the dark. Because it looks like a thick storm cloud, you might think an explosion there would create a massive boom. But in reality, a nebula is incredibly thin. It is more of a vacuum than the best artificial vacuums we can create on Earth. The gas is only visible because it spans trillions of miles and is illuminated by newborn stars. If you were inside a nebula, you wouldn't even know it. It would look completely transparent. And yes, An explosion here would still be completely, perfectly silent. The illusion of density is just a trick of cosmic scale. The concept of the mean free path. To truly grasp this silence, we must understand a term called the mean free path. It sounds complex, but it is deeply simple. Imagine an illustration of a single, lonely atom drifting through the blackness, with a dotted line tracing its long, uninterrupted journey. The mean free path is the distance a particle travels before it collides with another particle. In the air in your room, this distance is a microscopic fraction of a millimeter. Particles hit each other constantly, transferring sound instantly. In deep space, the mean free path can be millions of miles. If an exploding star pushes an atom, that atom will travel for years before it bumps into a neighbor. The acoustic wave dies before it even begins. The energy just fades into the lonely dark. The silent shockwaves of dying stars. If there is no sound, how do explosions in space affect their surroundings? They create something called a bow shock, or a silent shockwave. Imagine an illustration of a speeding boat moving through calm water, pushing a silent V-shaped wave ahead of it. When a supernova explodes, it flings a shell of plasma outward at tremendous speeds. This plasma physically rams into the sparse interstellar dust. It sweeps up the scattered atoms like a cosmic snowplow. This silent collision compresses the gas, heating it up until it glows brightly. This is how beautiful supernova remnants, like the Crab Nebula, are formed. It is a colossal, violent collision of matter, producing breathtaking light and heat, but refusing to offer even a single whisper of sound. Expanding the mind. What if space had air? Let us try a fun thought experiment. What if the universe was actually filled with breathable air, just like Earth? Imagine an illustration of the entire solar system enveloped in a soft, misty blue atmosphere. How loud would the universe be? The answer is terrifying. The sun is essentially a gigantic, continuous nuclear explosion. If space were filled with air, the roar of the sun would travel across the millions of miles to Earth. Scientists calculate that the sound of the sun would reach our planet at about 125 decibels. That is as loud as a rock concert or a train horn, constantly blaring day and night every second of our lives. The silence of space is not a deprivation, it is a necessary shield that protects our sanity. The friction of a filled universe. There is another reason we should be thankful for the cosmic vacuum. If space were filled with a medium thick enough to carry sound, everything would grind to a halt. Imagine an illustration of the Earth struggling to push through a thick, syrupy fluid, its orbit slowly shrinking. Air creates drag, it creates friction. If the solar system were filled with air, the planets would constantly push against it as they orbit the sun. Over time, this friction would slow the Earth down. Our beautiful blue planet would lose its orbital speed and slowly spiral inward, eventually burning up in the sun. The silent vacuum is a frictionless playground. It allows the planets to dance around the sun for billions of years without ever slowing down. Silence is the secret to their eternal motion. Planetary acoustics, the muffled sounds of Mars. The vacuum of space is silent, but what about other planets? Let us travel to our rusty neighbor Mars. Imagine an illustration of a rocky red landscape under a dusty peach-colored sky. Mars has an atmosphere, but it is extremely thin. It is mostly carbon dioxide, and it is about 100 times thinner than Earth's air. How would an explosion sound here? We actually have data for this. Because the air is so thin and cold, sound travels much slower. High-pitched sounds are absorbed quickly by the carbon dioxide. If you heard an explosion on Mars, it would sound deep, muffled, and distant. A sharp crack would become a soft, heavy thud. The thin air of Mars steals the energy from sound, creating a strangely quiet, muted world. The Mars helicopter ingenuity. We don't have to guess what Mars sounds like anymore. We have actually listened to it. let us debunk the myth that Mars is completely silent. Imagine an illustration of the tiny, robotic helicopter Ingenuity spinning its blades rapidly above the red dirt. The Perseverance rover has a microphone, and it successfully recorded the sound of Ingenuity flying. But the recording is astonishingly faint. The blades spin at thousands of revolutions per minute, which would be incredibly loud on Earth. On Mars, the microphone barely captured a low rhythmic hum. The thin Martian air simply cannot hold on to the sound. Listening to this faint hum is a profound experience. It is the first time humanity has truly heard the acoustic heartbeat of another world. Planetary acoustics, the crushing noise of Venus. Now, let us travel closer to the Sun, to the hellish world of Venus. This is the opposite of the cosmic vacuum. Imagine an illustration of a thick, swirling, yellowish atmosphere glowing with intense heat and volcanic lightning. The atmosphere of Venus is incredibly dense, 90 times thicker than Earth's. It is a crushing ocean of carbon dioxide. How would an explosion sound here? Because the air is so thick and heavy, sound would travel much faster and further. An explosion would be terrifyingly loud. The dense gas would carry the acoustic energy with brutal efficiency. The roar of a volcano on Venus would travel for hundreds of miles, deep and distorted. Venus is a world where sound is aggressive, heavy, and inescapable, a stark contrast to the peaceful void above it. The stormy depths of the gas giants. Let us venture further out, to the colossal gas giants, Jupiter and Saturn. Imagine an illustration of deep, swirling bands of brown and white clouds plunging down into infinite darkness. These planets have no solid surface. They are vast oceans of swirling gas and crushing pressure. Here, sound waves would behave in bizarre ways. Deep inside Jupiter, the hydrogen gas is compressed so tightly it behaves like a liquid metal. A massive electrical storm or a meteor impact deep within these clouds would create pressure waves that travel at immense speeds. The sound would be a constant, deafening rumble of chaotic storms. If you could somehow survive the pressure to listen, the gas giants would be a symphony of deep, violent bass notes, echoing through an endless cloudy abyss. Titan's thick frozen atmosphere. Let us visit one of the most fascinating moons in our solar system, Saturn's moon, Titan. Imagine an illustration of a freezing, golden world with rivers and lakes of liquid methane. Titan is unique because it is the only moon with a thick, substantial atmosphere. In fact, its atmosphere is thicker than Earth's. Because the air is thick, but the temperature is hundreds of degrees below zero, sound here would be very strange. It would travel slower than on Earth, but the dense air would carry it well. A splash in a methane lake, or the rumble of an ice volcano, would sound deep and resonant. If you stood on Titan, you wouldn't experience the silence of space. You would hear the strange alien noises of a frozen, hazy wonderland. The Big Bang. Was there a sound? Let us go back in time, all the way back to the very beginning, the Big Bang. We often picture it as the ultimate explosion. Imagine an illustration of a blinding white point expanding outward, filling a dark screen with the universe. The myth is that it must have produced the loudest sound ever. But was it really a bang? At the very moment of creation, there was no space for sound to travel through. Space itself was expanding. However, as the universe grew and filled with a dense, super-hot soup of plasma, sound waves actually did form. For the first 380,000 years, the universe was thick enough to carry sound. It wasn't a sudden bang, but a deep, resonant, growing roar of unimaginable proportions. The primordial soup and early acoustic waves. Let us dive deeper into that early roar. Imagine an illustration of a glowing, dense fog, rippling with subtle waves of heat and gravity. In this early universe, light and matter were tangled together in a dense plasma. Gravity tried to pull the matter together, while the intense heat pushed it apart. This constant tug-of-war created massive pressure waves, actual physical sound waves. These waves cascaded through the plasma, compressing it in some areas and stretching it in others. The entire universe was ringing like a colossal cosmic bell. It was a symphony of creation, playing out over hundreds of thousands of years. But as the universe expanded, it cooled. The fog cleared, the vacuum formed, and the great ringing finally fell silent. The visual echo of the first sound. We cannot hear those primordial sound waves anymore, but remarkably we can still see them. Let us look at one of the most important images in science. Imagine an illustration of the cosmic microwave background. It is an oval map of the universe, dotted with tiny spots of red, yellow, and blue. Those colored spots represent slight differences in temperature. But here is the secret. Those temperature differences were caused by the ancient sound waves compressing the early plasma. When the universe cooled and the vacuum formed, the pattern of those sound waves was frozen in time. The cosmic microwave background is essentially a fossil of the universe's first sounds. We look through our telescopes and we see the visual echo of a roar that faded billions of years ago. Exoplanets with exotic atmospheres. Let us turn our imagination outward to worlds far beyond our solar system, exoplanets. Imagine an illustration of a terrifying world, HD 189733b, where it rains molten glass sideways in raging winds. The acoustics of the universe are as diverse as the planets themselves. On a planet like this, the roaring supersonic winds pushing the glass rain would create a high-pitched, deafening shriek. On a water world, entirely covered by a deep, planetary ocean, explosions or tectonic shifts would travel incredibly fast through the water, creating deep, echoing groans that could circle the entire globe. The silence of the vacuum separates 1 trillion tiny, noisy snow globes, each with its own unique atmospheric symphony. Space keeps their chaotic songs isolated. The psychological weight of profound silence. Let us bring our journey back to the human experience. How does absolute silence affect the human mind? We might think we crave total silence to relax. Imagine an illustration of a person floating alone in a vast, dark sensory deprivation tank. In reality, humans find pure silence deeply unnerving. On Earth, we are used to a baseline of background noise. When astronauts experience the deep quiet of their suits or the isolated corners of a space station, the brain sometimes tries to fill the void. It invents sounds. It focuses intensely on the rushing of blood in the ears or the beating of the heart. The profound silence of space reminds us of how truly isolated we are in the cosmos. It demands respect. Finding peace in the cosmic quiet. But this silence does not have to be scary. It can be incredibly liberating. Let us change our perspective. Imagine an illustration of a calm observer sitting on the moon, looking at a beautiful silent Earth rising over the horizon. When we let go of our need for constant stimulation, the silent universe becomes a canvas for meditation. An explosion without sound is no longer a violent assault on the senses. It is simply a transformation of energy, a beautiful display of light and physics. The silence of space teaches us to observe without reacting. It invites us to watch the majestic clockwork of the galaxies with a calm, undisturbed mind. It is the ultimate sanctuary for peace. Gravity waves as true cosmic sound. As we conclude our exploration, let us reveal a new kind of cosmic communication. If mechanical sound cannot cross the vacuum, how do the heaviest objects speak to each other? Through gravity. Imagine an illustration of two black holes spiraling towards each other, sending ripples through a grid of space-time. When massive objects collide, they don't make a sound. They distort the very fabric of space and time. These are gravitational waves. They travel at the speed of light, stretching and squeezing everything they pass through, even Earth. We have built massive detectors like LIGO to feel these silent ripples. It is a new way of listening to the universe, not with our ears, but by feeling the silent heartbeat of space itself. Our journey through the silent vacuum is coming to an end. We have seen why the grandest explosions in the cosmos remain forever mute. We have debunked the loud myths of Hollywood, understood the true nature of a physical vacuum, and explored how different atmospheres change the very fabric of sound. As you slowly drift back down to Earth, feeling the comforting, dense blanket of our atmosphere wrap around you, take a moment to appreciate the noise of your world, the rustling wind, the distant traffic, the sound of your own breath. The universe is unimaginably vast and perfectly silent, making our noisy little blue planet a rare and beautiful sanctuary. Thank you for taking this relaxing voyage with me. If you found peace in the quiet of the stars, please like, subscribe, and share this video. Before you go, tell me in the comments, if you could safely stand on any planet to listen to its unique sounds, which world would you choose?